Okay, now we're going to do case 5 from chapter 9. The data is going to be downloaded from case 2. Case 2 is the equivalent of case 5. With the exception of case 2, we assume the population variance or standard deviation is known. So I'm going to open up case 5. And I've already downloaded and copied and pasted in the data from case 2. And if you notice, all 25 of us, we all have different data because we all have different samples. Our sample size is 49, and all of us have a unique set of 49 numbers here. So we're simulating the idea of multiple sampling. For that reason, the sample size, again, n, is 49. Now the first step of solving the problem is, of course, to read it. So in recent years, the IRS has been inundated with taxpayer calls and has redesigned its phone service as well. An average wait time of fewer than 12 minutes is the goal of the new system. Using data here, can you conclude that the actual mean waiting time is less than 12 minutes? Now in part A, we want to state the hypotheses, right? The null or the alternative hypothesis is stated in the problem itself. And what I'm going to do is I'm going to highlight actual mean waiting time here. I'm going to change it to red and bold to make it stand out. Then less than, I'm going to make that bold. And then I'm going to bold 12 and change its font to blue. When we reread this now, it's pretty obvious that this is the alternative hypothesis because it doesn't include equals. So our alternative hypothesis is mu less than 12. Another way to state that is to state it as mu minus 12 is less than 0. So why do I do that? Because this is a sigma unknown problem. We have to use the test statistic Tstat. Because sigma is unknown, we have to use an estimate for the sample standard deviation. And the numerator of the Tstat is the point estimate of this difference. The 12 is the manufacturer's claim. We can't know the population mean mu, but we can estimate it with our sample of data here. We have our sample data, we can calculate the sample mean, and we use that to estimate the population mean. So the reason why I rewrite this as this equivalent statement is because the point estimate of this version of the alternative hypothesis is the point estimate of the difference, x bar minus mu 0, in this case 12. Okay. Now the null hypothesis is the opposite of the alternative. It is mu greater than or equal to 12. The null hypothesis always includes equal, and equal is kind of like the benefit of the doubt. So the null is always given the benefit of the doubt, the equal. Alternative tells us what kind of test it is. It's a lower tail test, is it an upper tail test, or is it a two-tail test? In this case, the alternative hypothesis is saying this is a lower tail test because we're talking about mu less than 12. Okay, now since the alpha is given to be 0.05, significance is alpha. Alpha is 0.05. It's a one-tail test, so what I like to do is I like to explicitly divide the alpha by 1 because it's a one-tailed test. That gives 0.05, which is the column of where we get the t-critical value from the t-distribution. We get the t-critical value from column 0.05 of the t-distribution. The degrees of freedom are n-1. Why? Well, we're estimating the sigma squared, the population variance, because we don't know the population variance. And in the sample variance, you divide by n-1, and that n-1 is the degrees of freedom. And in this case, the degrees of freedom are 48, because 49 minus 1 is 48. So we're going to get the t-critical value, the value that goes in this box here, from row 48 and column 0.05 of the t-distribution. And we're in column 0.05, we're in row 48, which corresponds to our degrees of freedom, n-1. the value, the t critical value is 1.677. So I'm going to copy that and paste it right here. Now, before I move on, I want to go back to the alternative hypothesis. The alternative hypothesis is mu less than 12. The population mean is less than 12. That means we have to have a negative t critical value. So we're just going to make that negative. Now the next step is to calculate the sample mean, because this numerator here is the difference in the point estimate of the difference between the mean and the manufacturer's claim. So we need to have the sample mean first, and the sample mean is denoted x bar. So I'm going to type equal average, because the sample mean is the average of our sample data. We have equal average A2 to A50, and then we hit enter. So that my sample mean is 15.44897959. Everybody in this class is going to have a different one because we all have different data. All these numbers vary from student to student. The difference in the sample mean minus the manufacturer's claim of 12. Right there, that 3.489795992, that is the difference between the sample mean and the manufacturer's claim. It is the point estimate of that difference. Note there is always going to be a difference. The probability that your sample mean exactly equals your claim is 0, because there's one value, there's 112 on the number line, but there's infinite many numbers along that number line that the sample mean could take on. Now the sample standard deviation is found by computing or typing stdev.s. .s is for a sample, .p is for the population. We all have samples of size 49. So we're going to use equal stdev.s and then A2 to A50. Okay, and my sample standard deviation is 2.344, and all the sample standard deviation is going to be different because we all have different samples, which brings up this idea that there's a distribution for the sample standard deviation, and all of them kind of pile up near the truth. Just like with the sample mean, we all have different sample means, but they're all kind of piling up near the true population mean. The standard error is the sample standard deviation divided by the square root of the sample size 49. Notice this is a little different than what I have in the Tstat. In the Tstat, I have the denominator here is the standard error. I have it as the square root of the sample standard deviation squared. The sample standard deviation value in F21 squared is the sample variance. And if I divide that by 49, my sample size, I get the same exact thing. Now the test statistic is the ratio of the point estimate of the difference and the standard error. In this case, our test statistic is 10.299. Because the test statistic is so much larger than the critical value, we have evidence against the alternative hypothesis. When we have evidence against the alternative hypothesis, we have evidence in support of the null hypothesis, which can be rewritten as mu, the population mean, minus 12 is 0 or greater than 0. Now because our test statistic is so large, we can actually say that our difference is positive and significant. However, our alternative hypothesis indicates that we're interested in a negative significant difference. In conclusion, given that our test statistic 10.299 is so large, much larger than the critical value, which implies that our difference is positive and significant, we cannot reject the null hypothesis at the 5% level of significance. If your boss has very little training in statistics, saying we cannot reject the null hypothesis of 5% significance is going to go in one ear and out the other. So what do we do instead? How do we phrase it in a way that people without statistical training understand this conclusion? Essentially, not rejecting the null is basically saying that the data suggest that the null hypothesis is true. So if that's the case, then the alternative hypothesis is not true. If you recall back to the original problem, an affirmative alternative hypothesis is we can conclude that the mean waiting time is less than 12 minutes. But because we cannot reject the null, we have to modify this statement as follows. We can not conclude that the actual mean waiting time is 12 minutes or less. In summary, for our case here, when we cannot reject the null hypothesis of hyperstatistical significance, we cannot conclude that the actual mean waiting time is less than 12 minutes. And that concludes case 5.